July 21st, 2023. This is the update on the Colorado Springs coils.
Okay, so this is a sequel presentation and demonstration by Eric Dollard and Adrian Marsh on the Colorado Springs experiment. This was an experiment first done in 2019 by Eric Dollard, and the coils were made by Bruce Gavin. We have made some subsequent adjustments to the coils, which I'll go through in more detail. So we're going to be demonstrating this whole system in operation using a different kind of generator, and looking at the kind of discharge that we can get from this system and power transfer between the red coil and the green coil. So this was originally done in 2019. Eric, you did a pretty large presentation on all the 1/20th scale model, everything at that time, and it was done at the 2019 ESDC. We also did some subsequent experiments using the multi-wave oscillator that involved Eric and myself. We also demonstrated some interesting single wire phenomena that you can get by driving the system from a disruptive spark gap system. So just to go through what we have here, so these two coils represent the 1/20th scale Colorado Springs experiment. They were put together at exactly the right scale, exactly the right calculations, all of the windings. They are all scaled correctly and accurately from Tesla's original Colorado Springs experiment. So this is a green coil. This is at the, nominally we call it the receiving coil, but that's not really how it is in a longitudinal mode, but we'll call it that just for clarity. So it consists of a 3-coil system. We've got a 2-turn primary here at the bottom with the copper. We have a multi-turn secondary coil with a shield ring at the top. Then we have a multi-turn extra coil with elevated capacity, and at the top we also have a breakout point on that capacity because we're going to be looking at a discharge experiment here. To tune this coil, we have a 1000 picofarad vacuum variable capacitor, that's a KP14, with a static mounted additional capacity, which increases the total capacity of this to around about 1600 picofarads. And that's there for us to be able to tune very accurately the two coils to be aligned with each other. So in between we have the single wire. This is a single wire cavity. That's coming off of the bottom of the secondary coil. So that's the bottom end of the secondary coil. Top end of the secondary coil is going to the extra coil. So this comes all the way across. This represents our longitudinal cavity between the two. Obviously in Tesla's era that would have been much longer, and it would also have taken into account a telluric cavity as well. He was doing these experiments through the Earth. So this is the, let's nominally call it the transmitter coil. It's the red coil. It is a reciprocal coil to the green, so it has the same design, same number of windings, it's a 3-coil system with 2 turns on the primary, multi-turn secondary, and a multi-turn extra coil with also elevated capacity and breakout point at the top. So these, and also has the same tuning capacitor arrangement that we had on the green coil. So it's a KP14 vacuum variable capacitor with a static mounted 500 picofarad capacitor, nominally about 15 to 1600 total capacity. The 2 coil primaries connected, there's a series connection, so it's 2 full turns, and that is then connected into the generator system. Now this is the same generator that we were using in the previous presentation that we did. It's a single GU5B Russian military triode. It's nominally about 2.5 kilowatt plate dissipation, 5 kilovolt plate voltage. It's a very, very strong, robust, and what we have found is that this coil very readily oscillates. So it makes for a very good power oscillator for this kind of experiment. And that's important to make the distinction between the experiment that we did in 2019 and the experiment we're doing now. So in 2019, this was powered by a high power linear amplifier at about up to about a kilowatt, and driven at the series resonant mode. So that was about 930
Somewhere around 900 kilocycles.
Around about 900 kilocycles. And in that experiment, there was a 500 watt bulb at the other end, and 500 watts of power was passed between the transmitter and the receiver, and that was able to light that bulb to full illumination. So 500 watts. And then you can do that in that kind of system, that kind of generator. It was a modified amateur radio transmitter that Bruce Gavin ran with a power output stage. Now this is somewhat different because now we're using a power oscillator. So we are tuning this oscillator to the various modes that arise, and those will be the parallel modes that arise from this interaction. And because you have 3 coils connected here, and they are connected by the single wire, so you end up with 3 parallel modes from this coil and 3 parallel modes from this coil. And when they overlap with each other, so in other words they are closely coupled by this single wire, then you end up with 6 overall modes. We are using here the first 2. So nominally this is now tuned to around about 1.1 megacycle.
Yeah.
We have a lower mode. I think you measured it, Eric, about 850.
Yeah, the mode that Tesla used was around 900 kilocycles. This seems to be running a little low right now.
Okay.
And but we didn't have enough capacitance to do that, so we're using the parallel mode, as you call it, at 1100 kilocycles. 1100
kilocycles.
And your oscillator seems well suited for that particular mode.
Yes, yes. It kind of readily, it is readily tuned and matched to that parallel mode around about that point. Yeah. There are also 2 higher modes that actually originate from the extra coils. We measured those up around about 1.6 megacycles, I think.
Yeah.
1.6 and 1.75. So there are 4 readily available tunable modes. There are obviously higher harmonic modes, but it's actually not that easy to get this kind of oscillator up at those high frequencies. So the generator is as we used before. So it is configured and connected in the same kind of way. We're using the same kind of parasitic suppression for harmonics and high frequency oscillation that Eric went through in the previous presentation. So things like the iron wire for the connection, important connections between the generator and the tank circuit, and obviously in the grid circuit. The high voltage power supply is the same one that we were using as well. That's basically the microwave oven transformer based amplitude modulated power supply. So altogether this is a self modulated AM or amplitude modulated generator. It's using a voltage level shifter, or commonly called a doubler, but it's actually a level shifter. So, and the output is for this experiment is between 3 to 4 kilovolts, and we'll be running the experiment up to around about 1.5 to 2 kilowatts. If we were to go higher, I mean we can go higher than that with a generator, but it tends to cause large arcs. The system has quite a high gain, or quite a high voltage inversion. So it's designed as a magnifying transformer, Eric. Yeah. So Tesla called this as Tesla magnifying transmitter, and that is what it's meant to demonstrate. We have, obviously, because it's a power oscillator, behind here we have a feedback coil. So this is a multi-turn selectable feedback coil which feeds the grid leakage feedback bias that the generator requires. This is now currently set to 11 turns of feedback, and we place that around about the same height as the secondary and not too far away. So we are picking up a small proportion of that signal being fed back to the oscillator, positive feedback, so it makes it an oscillator. And this is a Class C Armstrong oscillator. Eric, did you want to add anything more about how you calculated all the special characteristics of this setup?
Well, that was basically a lot of fooling around and flailing, but I finally came to the conclusions. So, what was wrong? So the variable capacitors didn't have enough capacity. These things are meant to have a big bank of capacitors. And the variable capacitors just to fine tune. So we got some patterns on there that at least get us down to the upper frequency mode.
Okay, good. These are these static ones added on the top here. And is there, I mean, you see a lot in people that are doing Tesla work where they're talking about equal weights or volumes of copper in the primary system. Is there any consideration of that here? Or is it important?
Oh, totally.
Okay.
Totally. Yeah,
okay.
The proportions, these proportions are exactly as Tesla, whether they were equal or not. This thing is, the relative weights and all that is exactly the same as Colorado Springs. These things are complete duplications to the finest detail.
Okay.
And the other thing that is kind of, when you're using like vacuum capacitors, oil capacitors, the capacitor should have about the same mass as all the copper of what it's driving. Shouldn't have any less than that.
Okay.
So the capacitor mass should be similar to the coil mass.
Okay.
When you're doing resonance circuits.
So we end up...
Because these capacitors are not rated in volts anymore, they're rated in amperes. Or in this case, kilovolt amperes reactive. So those disk capacitors are 40 kilovolt ampere reactive ceramic capacitors for probably dielectric heating or maybe broadcast transmitters. They came from the Eastern Soviet bloc, whatever countries those are today.
Yeah, these are, just to say again, these are KP14 Russian military variable vacuum capacitors with a customized mounting that was actually made in this research lab.
Because it's Russian, it's actually Kappa Pi.
Yes, that's right. Very robust. These are up to 10 kilovolts. Obviously, with the kind of magnification you get from this system, we've got to be very careful that you don't get arc over between the windings. During the tuning of this, we've noticed quite large streamers come out, and they tend to want to go down to the guard ring here at the top, or the shield ring at the top of the secondary coil. But for example, we had this piece of wire here that comes out from the top of the extra coil onto the master on the elevated capacity, and this was taking just a like a bow away from here, and that was enough to imbalance it sufficiently that it could actually cause a discharge down to the top of the shield ring here. And Eric, by actually bringing it very close here, you balance up that field distribution, and that stops that breakout.
That's what that little cap is for. That's the electrostatic shield.
So very small, fine details like this are very important in how you set the system up. It's the difference between the system just burning out on the secondary coil and actually running properly as it was originally designed. And I take it also, Eric, it was important that everything was exactly as Tesla did it, because otherwise we're not going to actually see what Tesla saw.
Well, it won't be reproduction.
Yeah, it won't be a TMT.
As exact as possible. Yeah.
Good. Okay, so that's nominally the system. We're also going to, in the second demonstration, we're going to use the high voltage, DC high voltage supply that Eric is in front of. That's the RF rack. So we're going to do a number of different types of experiments using different generator. I think we're also going to use the cathode keying modulation as well,
and the amplitude modulation with the music.
And the amplitude modulation with the music. So we are going to apply everything, all the variation that we've got from the different generators. We're going to apply that to this system and see what kind of effects we can create. We'll start with this generator. This generator is very suited to the power oscillator, and the power oscillator seems, we concluded, Eric, that somehow it seems to be quite suitable for this kind of arrangement.
Yeah, very well adapted for it.
Yeah, and also it gives us a degree of adjustment. We can adjust power, we can adjust tuning, and that makes very subtle changes and differences to the discharge. Now, just to say something about the discharge, I mean, previously we've been demonstrating things like the burning bush. Then we transform that into the tree. We also transform that into the root. We've also transformed that into the golden ratio or the golden dragon discharge. So by the way that you go about modulating and you go setting up the generator determines the kind of effect that you're going to get. And how you adjust those parameters determine very accurately the kind of interaction between these two coils, the kind of discharge, because nominally this system is not originally designed for making discharges. I mean, do you want to tell us, Eric, a little bit more about what Tesla's real intent for this system was?
The thing is Tesla was into the light show. The thing created a lightning storm, but that stuff all draws away from the actual power operation.
Yes.
Because that's a short circuit. You don't build a substation transformer to have to make big arcs all over the whole neighborhood.
Absolutely. You just discharge the power. You just lose the power.
It doesn't make any,
Yeah.
And that's what Tesla, he had to do whatever he could to make those discharges not happen.
Yeah. So, for example, in this system, if we were to take the breakout points off of the elevated capacity, then we'll find that the energy will stay in the system rather than actually discharging. But of course, then you've got to have something to do with that energy, because otherwise it's going to find somewhere else to break over.
Well, that's why then you really got to start amping up the kilovolt ampere reactive rating of all your parts. Because once this thing's not short circuited, it's that's when it's really cranking.
Yeah.
Really cranking.
Yeah.
About 1,000,000 volt amperes reactive. That's a lot. That's what Tesla referred to as the horsepower of this oscillator. So 1 million VAR would be like 130. It would be 1,300. Yeah, 1,300 horsepower. It'd be basically a megawatt.
Which is enough to power.
Well, not megawatt, but
small
megavolt ampere reactive. That's important. It's not megawatt. It's megavolt or it's kilovolt ampere reactive.
Sure. Okay, so this is our first demonstration. We've got everything warmed up. As I said before, we're using the self-contained amplitude modulated generator. For the first demonstration, we're going to be looking at the discharge that we can generate on the transmit coil, and then we're going to be going over and seeing how that translates to the receiver coil. So, if I turn on, we're going to start with a little bit of power, just so we get a very small discharge at the top there. That's only 100 watts. Gradually wind up. It's 250 watts. It's 500 watts. We're going to keep going up. So that's 1.2. 1.5. The 1.5 kilowatts of input power to the generator, and we see the kind of discharge we have. It's a very typical vacuum tube Tesla coil, swords type, very straight. We notice that we don't have any of those curvatures or the golden dragon or any of the tree or the root in the discharge. It's actually a nice spherically emitting fractal flow. Straight swords, and that's at around about 1.1 megacycle, and it's nice and stable. We can adjust the oscillator slightly just to make sure that we're in the best place. I'm going to release the bias. It becomes more noisy. Reduce it. It smooths off, becomes deeper in sound. Just optimize its position. So we are drawing about 250 milliamps plate current and about 45 milliamps grid current.
What's the plate voltage?
Plate voltage is just around 3 kilovolts. Okay, so this is what's going on. Everything's nice and stable. The transmitter. If you'd like to pan around and look at the receiver, we also see at the top we have a small discharge at the top, and Eric's going to demonstrate the kind of tension that we have on the tube.
That's what we don't want.
Okay.
Why the hell is it doing that? Man, that's a lot of voltage in there.
Let me, so let's turn the power down.
I think we're kind of off frequency.
Okay, so we just need to tune a little bit. I'll bring it up.
You know, this loose stuff in the middle.
I'll bring it up. We had a bit of a breakout here at the bottom of the extra coil, showing that there's quite a lot of tension there. So we're just going to retune slightly. Just adjust. Yeah, it was just slightly off. Very fine adjustments. that I'm making here. You can hear on the video, I hope you can hear just a slight change in tone of the discharge. It seems to be about the best spot there. So I did that about 400 watts. That's about 1.2 kilowatts. See what the discharge is like now over your side.
That's good what I did before in detuning. I don't want, I'm afraid that makes sparks on the
That's okay, I'll turn it off if it starts. Let me adjust the rise slightly. Right, I'll just increase the grid slightly so it's more stable.
That's when I started arcing, so
just try to low down just to see.
Here.
Yeah. Okay, that's better. I think it's better now.
Yeah.
So that's normally we're running here at about 1 point. That's better. We also have a streamer at the other end. We noticed that the streamers are not the same size. So in other words, we are not getting as much power on the receiver side as we are getting dissipated into the transmitter. So we'll just pause and we'll let the tube cool down because the airflow in this system is less than what would be the maximum required to run all the time. Eric, can you just explain to us why the discharges are different sizes at each end?
Well, this is dropping power from this.
Okay.
So basically, if we started the discharge here and tuned to that, conceivably it would be as big as that one.
But is there a condition where we can get to where the two discharges would be the same?
Yeah,
is it possible?
Might not be stable.
It might not be stable in that position.
Yeah.
I mean, was Tesla's original intention to be able to get as much power from here to here?
Yeah, but not necessarily mix sparks.
Yeah, not to make discharges.
Yeah.
And also, we have to remember we're using the parallel modes here. I mean,
that's not what he used.
It's not what he used the series mode.
Yeah, that's why we have that flash over. It's trying to operate in another wavelength.
Yeah.
It's trying to operate half wave rather than quarter wave.
And if we compare that to the original Colorado Springs in 2019, where the series mode was there, it was very clear that you could actually transfer almost all the power coming in to here. So Tesla would have been using it at quite a low frequency. What kind of frequency would he be operating?
He was operating around 45 kilocycles.
Around about 45 kilocycles. Did he choose that? Is there a reason for that choice of frequency?
Well, he doesn't really say, but it's been a lot of work getting to that frequency.
So he maybe had some kind of knowledge that somehow that was a good
knowledge.
That was a good band.
We don't have that knowledge, but he had plenty of it.
Yeah. In a way, we have to rediscover it.
Yeah.
Okay. So we can just run that again. Now it's cooled down a little bit. I'm gonna turn on now without winding up slowly. So we just see how well balanced and tuned the system is. Okay, so that was a good startup. When we tried that before without the good tune, then we would get a discharge, a very, very fast discharge coming from here down towards the guard ring. So I will just try that again. If we have the right balance, then we're not going to have that. Okay, good. So the system is nicely balanced at the moment. And we're drawing about 1.5, normally 1.5 kilowatts input, real input power to the generator. Nice and steady, small discharge at the other end. The lengths of these elevated capacities have also been adjusted to be balanced. Originally, first of all, we used the vector network analyzer to try to get the balance correct between these two coils. Very fine adjustments. And then Eric did additional tuning from the center point here using our master oscillator. Very nice, harmonious. That's the kind of discharge, that swords discharge you get from using a Class C Armstrong power oscillator in this scenario. Feedback coming from the coil. Okay, good. So that's the first demonstration. We're going to take a pause and then we're going to power up the high voltage rack here, and then we're going to move on to the next stage of demonstration.
Yeah, we got to get the other plug, and we got to plug the dummy load back in also.
Okay. Okay, so I've connected the rack behind. Are you taking out the shorting jumper or keeping it in for the moment?
Yeah,
you're keeping this in for the
We got
moment.
to keep that in, but we still want to go to the load.
Okay, so we've got to go to.
This thing wants to operate in between.
Put that in parallel.
And when the amplitude modulator is on, it will go back up to that voltage. It'll be about where we maxed out at 3,500 or what have you. As we went with this, I think.
Yeah. I don't think we want to go much above 3 kilovolts, because the 3 kilovolts it starts arcing in places. We want the dummy load back in on the modulator layer, just in case.
I always like to start with that. If
I
agree.
agree.
If there's a need for more power, then we can take it out.
Yep. Okay, so that's back in. You can power up this when you're ready, Eric. And also we can power up this one when you're ready.
Not lighting. And the scope's still not lit.
Oh, okay. Let me just check. I need to put the main power in. I'm just going to connect the main power. Okay. Should be good.
There we
now.
go.
The oscilloscope should be.
See, we got to hook that to the China box.
Yeah. Oscilloscope's on. Let's just turn this on. Let's see, where are we connected? That is connected.
And all of a sudden, we got some RF from somewhere. Where did that come from?
No, that's how this box never stores its settings. So it's come on with default settings.
Okay.
I have to reset it.
We can save it in the system settings.
Can we? Okay. We'll do that this time. So we start with 10 cycles, 10%.
10 pulses per second.
I did the same again.
Yeah.
Do you remember?
Well, you can't help it. I mean, it's just, it just seems natural to do that.
Okay, so 10 pulses per second, 10% GT. Now let me set the offset, so amplitude, up at 10, offset, up at 5. Turn that on, I should hear the relays clicking, which they are. Good, that's set.
You got it on the scope? Thinking timing.
No, I need to do that.
Yeah, it was indicating something, but you just got to fool with the sweep. There you go.
Triggered. Now we need another.
Yeah.
Let's see that in parallel.
So you need to make another one for that over there.
I can find something. You look and see. We've got steel. Steel one for this generator. I think it's which I can use on here. This one can come back. This one is actually the one for that. Eric, you plug that one back in. It goes across the top.
Yeah.
Right. So, for a moment we'll turn this off. We need to plug our high voltage in and our modulator. First of all, we set this first of all so it bypasses the modulator.
Yeah, that switch is on.
Okay. So here we just removed the connection between the cathode and the generator earth, and we're going to put the cathode keyer or the cathode modulator in at that point. We covered the cathode modulator in detail in the previous presentation. Eric talked about the mercury rated relays, everything like that. We don't need to cover that again now. And we need the high tension as well, which is down here. This is
Tangle that all
yeah, I think it does need to be.
Phosphating.
It's organised. We don't really want it around the HT. This one we don't need. Come out. This remote control we don't need. This can go back up there. Come around the other side, so the high voltage. Remove this. Right. So remove that there. So this connects. So we're just connecting the amplitude modulated supply, and we're going to put the DC, high voltage DC supply in its place. Okay, good. So we've connected the high voltage output from here, goes directly to the generator. Through the plate current meter, we still have the grid current connected in the same way. There. Okay, good. Okay, so just to note for this demonstration that we haven't tried this demonstration before, so Eric and I are really experimenting now. We just experimented to see what we can do. And so just to run over, so we have two coils connected in exactly the same way as the previous demonstration. They are tuned in the same position, so what we consider to be the optimum tuning that we can have for this system at this time. Connected to the GU5B generator, and the GU5B is fed by the high voltage DC RF rack that Eric is sitting in front of, and we also have the cathode key modulation going into the same rack as well. So we're going to, first of all, we're going to bypass the modulation, and we're going to see what kind of discharge that we can draw offer this system. Like I said, we haven't tried this before, so we're going to be ad hoc experimenting now. Okay, let me just check all connections one more time, make sure everything's tight. Okay, if you would just, Eric, if you want to just put it quickly and off and just see nothing arcs over.
That's good.
We had a lot of grid current, so I want to get that adjusted.
Okay.
Let me back it down a bit just to start with. Just very quickly again. That's better. That's better. Okay. Okay, so we have a small intense discharge. Let's see if we can optimize that in any way. Quite stable with the tuning. Let me just adjust the grid. Seems to be about optimum. It's about 60 milliamps grid. Let me see what if we have anything at the other end. We just get the tube. I think this might be consuming a little bit more too much energy. Okay, so there is some tension there. Yeah. Small discharge off of the elevation. The top there. No breakout at the top, but we would expect that because we're running at a lower end. We're running at 2400 kilovolts.
We're down to 2000 now.
Down to 2000,
Yeah.
are we? Okay, so 2 kilovolts plate voltage. So we were running about 3 with the other generator, but we have a nice stable, small plasma flame from the DC source. Yeah, just over 2 kilovolts it's saying here. What I'm going to do, Eric, if you just could turn off so that we don't consume any energy at this end. I'm just going to disconnect this for the moment. I'm going to leave it as a low impedance flying lead.
This would take a lot of tuning. You might want to connect it to the metal table.
Yeah, okay. We'll use that as a ground plane. Okay, just quickly, Eric.
You might have to go back to your other power supply.
Did you get anything at the top?
No, you're going to have to go back to your other power supply for the tuning.
Okay.
We're starting from scratch now, so let's go back. We're actually doing another thing now. We've transformed. Let's go back to your other
Do you
power
actually want to
supply.
put this one in and then we do the modulation first? Because I can put this back in.
Yeah, let's just do that.
Let's just do that first.
Yeah.
Eric, if you could turn on again, just make sure we had what we had before. Just quickly. Yeah. Let me just optimize that a little. Things have changed slightly. Better. Okay, when you're ready, you could switch over.
Not kidding.
Turn off.
Wait a minute. I got the cathode voltage. The relays don't seem to be clicking.
Okay, just turn off for the moment.
Okay.
Let's just check. I can hear the relays.
Yeah. And I got voltage here. Maybe it's just that.
Not enough plate. Not enough
well,
plate.
I don't know what's going on.
I suspect we haven't really got enough plate voltage.
Well, let's see if it's.
Do we want to put it in series and
Well,
try?
let's go back to where we were. Get the light up again.
Okay.
Okay.
Yeah, it's good.
Okay. Now
Maybe we put it in series now, because we don't really have enough up the top there.
it's not pulsing. For some reason, the relays are not contacting. This box might not be putting out enough. 5 volts. You want to go to 10.
No, it's on 10.
Is it?
10 with an offset of 5. I don't think
No, it's flashing. It's pulsing.
Pulsing?
Yeah.
Do you want to increase the output of the high voltage supply to the 4 kilovolts?
Yeah, let's try that.
Okay, all right, you turn off.
Okay.
Because I think we need a bigger discharge at the
Yeah.
top end.
Yeah.
It's not really big enough to get this lit. Okay. Everything off?
Yeah.
And we've got the modulator still shorted.
Yeah.
Okay, so we're going up there, down to there, down there. Okay, so that is now nominally 4800 volts plate. So we've put the 2 high voltage DC supplies in series. They were in parallel before. Let me just wind it, let me just ease it off a little bit.
Go back to CW.
Go back to CW. Okay, just very quickly so we can see the meters.
Flame.
Okay, I need to adjust a little bit though.
Okay.
If you could turn on but ready to be turned off. Let me just get these. That looks about okay. Let me just adjust here. Now that's pretty good. Actually, let's just look at that flame. So that flame there, that plasma flame, that's the burning bush, which is actually nominally about the same size as we got with the previous presentation that we did with the golden ratio discharge coil. Just hold on a second. So we are running, let me just back that grid voltage down a bit.
Yeah, kind of.
So 70.
Turn it down a little bit if you can.
Okay.
You go to pulse, it's going to want to lash out.
So I'm going to back that down to about 60 milliamps grid. Just turn off a sec. Just a little bit too much feedback. So I'm going to take a turn off of the feedback coil. It's pushing the tube quite hard. Let's back that off. Okay, just try that quickly, Eric. Okay, that's better. That's 50 milliamps grid. And we've got 400 milliamps plate current. That's pretty good, I think.
Yeah.
It's in the middle of its operation. So we just took one turn off of the feedback coil here. Just try that one more time. Okay, and off. Okay, so we've got the system in the middle of its characteristics. We are still using the counter. Let me just see how much tension we have over here. Eric, if you could turn on. Very little. Oh, no, we can draw.
It's burning my fingers on the rack, so we're transmitting.
Yeah, we can draw a bit off. Okay, and off. Okay, so really, in this scenario, we are using this system as a counterpoise. It is basically a counterpoise balance for the transmitting coil. Okay, so I think the next demonstration is to put that on, and then we switch over to the modulation. So when you're ready,
Yeah, I'm going to not switch it mid-span. I was going to turn it on.
yeah, turn it on.
Here we go.
There we go. Okay, we're just going to have to look at optimizing that a little. Okay, a little more aggressive. Let me just tune that a little. See also what we've got coming over, if we've got anything coming over in the counterpoise. So a little bit through the flashing according to the pulsing.
Here's the problem when we're operating in this mode and trying to get to go between the coils. In the normal mode, these 2 coils constitute a half wavelength.
Yeah.
In this upper mode, it constitutes 3/4 of the wavelength.
Yes.
And that's why that coil lashed out from the middle, not the edge.
That's right, because it had a shorter wavelength.
There's a hot spot there. So
Yeah.
the wave is bent right now because you can't get this thing down to the fundamental frequency.
Yeah. You can see the pulsing in the single wire. All the way along the single wire, longitudinal mode. Always comes off the test transformer. Quite intense on there.
And if you try to fit it for like more snappiness and
Yeah.
variation.
Yes. So, first of all, the tube a little harder. I'll try changing the pulsing. Maybe we just go let the tube. Also, it would be nice to see it go from the burning bush to that.
I don't like making that transition.
Okay.
It did something funky. I don't want to.
Is it too much pressure for the mercury weighted relays? Something.
It screwed up then. I don't want to.
We don't want to encourage those things that can somehow come along and blast something.
Something snaps at me, I back away.
So we're just going to let the tube cool down a bit. I mean, if you had this in, we have airflow of around about 60 cubic feet a minute of airflow on there. Nominally, this tube will, if it's running in continuous operation, will need about 200 to 250 cubic foot a minute on the anode, and it's going to need about 1/10 of that, so somewhere around about 25 cubic foot a minute on the grid electrode and the electrodes at this end. It needs quite a lot of cooling, this tube, for its size. Okay, so if you want to go back on, Eric. Now we're going to adjust the pulsing. So we are 10 pulses a second currently. We are going to go downwards, upwards, we're going to go down. 8, 7, make it, we'll adjust the duty cycle as well. 5% duty.
Most of the time we've seen the frequency back and forth and see what kind of snapping it is.
Okay, so we're on 5 pulses a second, 5% duty. Easing it off. Faster. We're going to increase the cycles per second. 10,
That's good right there.
that's 20, that's 30. Yeah. We were up at 50, 40, that's 30. We didn't keep it up too long at 50 because it will start heating the tube quite considerably. What we put it at, Eric? Okay. 20. Up there? Ah, yes, okay. I'll just take the duty down a little bit then. That one, yeah. So again, we're looking at the external for the tree and the roots. You can adjust the grid bias. To do that, we will need to get that effect with tree and root because the counterpoise is balancing out.
Yeah.
We're going to need to disconnect the single wire, retune it so it's on the ground plane. Okay. If you want to turn off, Eric. You see it had kind of faded down.
No, I didn't. I was watching this.
I'll turn it back on a second. Okay, now watch up there when you turn it off.
Yeah,
It kind of like goes back where it came from.
Yeah, I found that what's going on. This switch is a little sticky.
Oh, is it? Okay.
I think so, yeah. It's only 100 years old.
So what we're going to do now, what it seems to be, is that this coil is acting actually as a very effective counterpoise. So therefore, as I start to tune there, to change it, it's actually being balanced out by what's happening at this end. So when you've got waves going backwards and forwards here, as I adjust this, this is actually not auto-compensating, but balancing out what's going on between the two. So in order to adjust the frequency more accurately on this, we're going to disconnect the counterpoise, or the reciprocal coil. We're going to retune with using the table, the metal tabletop here as a virtual ground plane.
Now you got to go back to your power supply.
You're going to use my power supply to tune
Yeah.
this? Yeah. Okay. All right.
We
So
don't
you
want to be hitting this thing with any full power, while we're tuning.
just to check. Did you want to do any of the modulation,
No,
Dave, before we
not
go?
until we got this
Not till we got this right. Okay. So you're off there. Huh?
Yeah.
So what we're going to do is, because we're going to use this as a virtual count plane, we're going to take the counterpoise out so we can tune a larger range on this coil. Then we're going to put this generator back in, because this generator is very suited to find the center frequency before we actually use the high voltage rack and then the audio modulation rack. So again, I'm just going to disconnect. I'm going to keep that wire installed here because we're going to use it. I'm going to put the self-modulated stop those relays. Okay. Okay, so we've reinserted this self-amplitude modulated generator, power supply. And we're going to retune this system to work just with the one coil and this virtual ground plane. Is it bypassed, Eric?
Yeah.
Okay. Alright, so let me ease it off a bit so it's not so aggressive. Breakouts. So I'm going to put that back up on one. Let's see what we can get.
It won't work without the counter coil. Good.
Yeah.
But it might be this one just have enough capacity.
Something's not right here.
Yeah, maybe we shouldn't do it like this.
No, let me just check everything is properly connected. Table, this wire here. Now, do you have a small piece of plastic like this, please? Because we're using the table now, so we need to be careful what's on the table. In actual fact, I'm going to use this much better ground wire. Thick ground wire down to the table. I can see that the tube's there's hardly any grip.
Yeah,
It's not
the
oscillating.
feedback phasing has probably changed because now you're operating in a different, standing wave configuration.
Yeah. Good connection down. What we did is we took away the long, thin single wire of the tube and we put in a nice 12 gauge connection down to the ground plane. Right, my attention. Feedback coil. So basically we are having, because the table will now become hot as a ground plane, electrically hot, we're having to reposition wires from the experiment to make sure they're not coming in contact and creating a corona around the wire or some kind of possibility for a flashover. Alright, let's give that another try now. Okay, so we give that another try. That's better. Okay, let's do so I get some tuning. current, stabilise. Plate current's not bad. Let's try going up a little bit more. So 1.8, 1.5. That's 1.5. Let me just check. Knock the feedback down a little bit. Let's just try that again.
More feedback.
Yeah, it's a little bit more. We can go up one. Just try one either side. Yeah, grid current is better now. Let's get back to 1.5. Nice sound.
See,
Now
you can hear the difference between the magnetic and the dielectric we couldn't before.
Okay, do you want to just talk about that because it's something we haven't covered yet?
You were on? Yeah, before you could only hear the snappiness of the dielectric, but now you can hear this kind of humming when we go into the magnetic. Go back and forth a couple of times.
Okay. Okay, so let me go right down to the magnetic. There's the magnetic.
Yeah.
It's a deep sound, and that's because the magnetic induction field is dominant in this system. We go the other way. There we're changing. That's about the optimum position. The two are equally balanced. We go the other side. We get that snappiness now as the dielectric induction field is dominant on this elevation.
Now go back to the magnetic so you hear the transition. Go back right there. There's a funny sound.
Yeah.
Nasal.
Yes. It's like a nasal, deep kind of nasal, like the magnetic.
Go a little lower.
That's as far as you can go.
Is it?
Snappiness. So it's also really important that the difference of the sound of the discharge actually tells you a lot about the balance between the two induction fields in the system. So now we should be able to do the tree and the root now.
Yeah.
Okay, so what we're going to do is we're going to set in an optimum position, say about there, 1.5 kilowatts. Just check this tune. Yeah, I think that's the best position. Okay, so just to recap, Gary, could you just put the lights on, please? HG off. So what we've done now is we've taken just the red coil and we've retuned it to work with the metal virtual ground plane that we have here, and we've demonstrated a difference between emphasis between the magnetic induction field and the dielectric induction field. One is very deep, and it's a kind of nasal, kind of very kind of low frequency sound. And the dielectric induction field, when that's emphasized, it comes snappy. You hear that kind of cracking and snapping, and it's not because the system is not tuned properly. If the system were not tuned, you'd hear pops and cracks as the oscillation stops and it restarts. So the system is stable, but we're just changing the balance of those two induction fields. Okay, so what we're going to do now, we've got the tune in the right place, we're going to reconnect the high voltage DC supply, and then we're going to go back and see whether or not we can start with the burning bush, and then we're going to move on to the pulse modulation, the cathode key, and see if we can get the tree and the root in this system. Okay. Go off for a moment. Actually, the main difference was putting this, Eric, in there.
Yeah.
Thick.
A lot less resistance.
Yeah. So it really becomes much more like a quarter wave system.
The interesting place to put that current probe.
Yeah.
Later.
Yeah.
Yes, how much every time we got.
Okay. Let's see this. It comes out. This one goes in. good. Check. Away. Okay. And that's it. Okay, so first of all in bypass.
Yeah.
Modulation in bypass. Oh, we need to turn on the. We've got that 20 cycles. Maybe we take it back down to 10. We've got
5. 5 seems to be.
Let's start at 10 because we always start at 10. We've got a 3% duty.
Let's go back up to at least 5.
Okay, so duty, I'll take back to 5. Okay, so let's turn that off. Okay, so first of all, let's just see where we sit. I'm going to back it off a little bit first of all. Just a quick flick. Okay, that's quite close. Let me just adjust the grid. I'm going to back that off a little bit.
Throwing some heavy current now.
We're doing 400 milliamps plate current. Okay, that's good.
So
nice stable burning bush. Let me just check the tune now.
Do you have a voltage reading? That voltage?
4.1 kilowatts.
Okay.
I think that's quite good. Do you want to go over to the, would you, that's it, switch over to the pulsing. Let's optimize that a little bit. There. Just need a little bit less feedback if you just turn off. Just going to take that down one turn. Okay, try again. That's in about the middle of its characteristic. Just let the system cool down. Okay, what did you want to try?
Well, the next would be AM.
So we move on to the modulation.
Yeah. But in order to get the burning bush, we're going to have to keep it on the higher voltage, which is okay. Well, I can't turn the modulation up 100% because that doesn't put out enough voltage.
Okay, so we'll just keep it turned down a bit.
Yeah.
Okay, so if you go back to bypass, let's just get ourselves set up best for the burning bush to start with. So let me just make this a little bit less aggressive. Okay.
Well, actually, why don't we start off with the AM at its normal voltage? And then we'll go back up.
Yes, I agree. Okay, all right, so if you turn the power supply off. Okay, so what we're going to do from here is we've done the cathode key experiment. We've shown the balance between the emphasis of the magnetic and the dielectric induction field and the effect that that has on the system. We've shown a one-coil system with the ground plane, we've shown with the counterpoise, and we've shown Tesla's magnifying transformer configuration. So from here, what we're going to do is we're going to add the audio modulation rack that Eric is standing by now. Eric, you might just like to say what that is, what it's about.
Yeah, this is the plate modulator for the RF system. So this superimposes the audio frequency high voltage on top of the high voltage direct current and then feeds it to the amplifier or power oscillator too.
Okay, good. So in effect, that is it's a series-driven modulation.
Yeah.
Okay. So we have these two connected. Are we going to use just the audio frequency first of all?
Yeah.
Okay. So this we're going to put down also to half voltage to start with.
Yeah, this to start with.
Okay, we'll just do that. Just checking everything is off. We'll turn off the keying. And we go back to parallel connected. So one to the top. One to here. And I'm going to remove the modulator bypass.
Yeah.
Okay, good. And we have the dummy load connected as well.
Yeah.
Do you want to get a display on here of the modulation, like we do? Something? Do you want to see it on the scope?
No, I don't want any more complications right now. Well, actually, it wouldn't hurt, but
I can arrange the coil here.
yeah, let's try that.
Okay. Just explain what that produces on there, Eric.
Yeah, that's how we're going to measure the percentage of modulation. As we go above 100%, then everything starts to get over voltaged.
So you're going to use a small pickup coil here. This is a few turns. It's actually almost 3 turns of insulated copper wire onto a long coaxial cable, and we're going to put that close to the pickup system here. So that will give us a measure of what the signal looks like, so that we can see the degree of modulation. That helps Eric basically adjust the overall signal so that we don't over-modulate or under-modulate. Okay, so that is in place.
We've got to change the scope connection.
Yeah, we reconnect that. Off. There we have one here. So that's connected. Just keep this sensitive there.
So I think the first thing to do is let's just start off with the burning bush carrier. And
So
then
you
I'll
can adjust
this.
this. Okay. So that is now in the burning bush will be very small now
Yeah.
because we're just in parallel. First of all, if you just want to turn it on very quickly and off,
Okay,
just check. Okay, everything's okay here.
Yeah.
So now we're just getting the equipment set up so that we can see the modulation.
So now it should be all ready to go.
Do you want this a little bit faster, or
Well,
are you happy with that?
yeah, I'm happy with that. It's all the harmonic distortion that's making it.
Maybe turn it, slow it down a little bit.
Then I can't see the.
Okay, you adjust it to where you want.
Yeah.
Okay.
Okay, here we go.
Hang on, let me come round here first. Okay, so we're going to introduce. There we go. We can hear the signal. We can see the discharge is getting bigger. Eric, if you could put a fixed tone on, I just want to try adjust the tuning a little bit here. Let me just optimize that. That's about there. Let me just adjust the tune. Okay. Okay, that's good here.
Okay, that's good. The next thing now, let's do some basic audio here. Okay.
What frequency is that?
400.
400 kilocycles.
No, 800. 400 cycles per second. That's 100% modulation.
Okay. 2750 volts on the plate.
Because I remember the modulator is doubling the plate voltage at the peak.
Absolutely.
4,000.
And also we see how nicely it's coming out.
Yeah, that's why I want to try it with the music.
Yeah, that's coming out very nicely as a...
There's no stability problems anymore. This thing's cranking out full power just the way it's supposed to.
I've just been, you've got the dummy loading too, remember?
Yeah, I know, but I'm still getting over 100% modulation.
Okay.
Now we can go to the CD player.
Just turn off the high voltage. Eric, let the shooter cool down. Okay. I don't think we actually need it in series at 4800. Do you think?
Well,
do you want to go 4800
later? Yeah.
Later. Okay.
Yeah. I got an idea here. So.
Okay. Go on. Explain what you're thinking.
Oh, because the art is changing with the music or the tones. I want to see what the bird looks like and then the music.
Okay.
And we don't need the protective apparatus anymore because now we don't have an instability problem.
Okay. So we need to bring the oscilloscope down here. And we need to bring the speakers and the system up here.
We need one speaker for a monitor.
Okay.
And the
All right,
battery and the CD player and just one channel straight in.
Okay.
No, how would you say?
All right, so what we're going to do is we're going to set up now to play music from the music system we have here directly through the modulator, and then that will come directly in the flame, and then we see what we get when we experiment with that. So we have to change a bit around here. You're going to continue? Okay.
All right, so let's move this. So let's get rid of this box first.
Eric, if you could stop this thing from doing a kind of like light show.
It can't help itself.
Oh, never mind.
Okay, and that's without the resistor. Where's the volume control?
That's with the resistor. That's without the resistor.
Yeah,
sorry.
okay, it's bypassed, right?
Yeah, you can adjust the volume by turning the knob. It's bypassed. Okay, so what we're going to do now is we've got the audio modulator bay connected to the high voltage source, connected to the experiment, the same as it was, and you can hear Eric's basically tuning up to play audio directly through the flame.
Okay, now I can bypass the light bulb. Temporarily. Okay, so ready?
So first of all, let's so this is first of all in parallel 2400.
Yeah.
We strike the flame first of all,
Yeah.
and then you want to go to your bit there. Okay, so we need to turn the high voltage here on here first. Let me just get down here to check the meters. Okay. That looks good. Okay, so So the bird sounds that you're hearing are coming directly from the flame. And one of the things that you won't be able to get necessarily on the film is the spatial effect. It sounds like surround sound.
Yeah. I want to show the dummy load blinking. Yeah.
Okay, Eric and off.
So let's let it run for a while.
Okay.
It's a pretty pure sine wave. Give the tube cool down a little bit. Yeah. That's the one I wanted.
Okay. It's got a bit longer.
Okay. Cool down.
Yeah. And the high voltage. Okay, so you want to go to series?
No, I want to go to the violin.
For violin first of all.
Yeah.
Then we try series.
Yeah.
Because then we should get a
Then we'll
big.
go back over again, start over.
Yeah. Okay. Okay. All right. Let's give it. We need to give it about 2 minutes for the tube to cool.
Okay, let's get the thing set up for the other piece of music.
Okay. Yeah.
That one is, I think that's number one, I think. Yeah, but we got to get the fugue out of the whole. We got to let the
What I'll do
prelude go.
I'll take it. I'll take it to a point where we'll pause it.
Yeah. It's like about a 1 minute prelude.
Well, you tell me when to pause.
Yeah.
Well, you can press that button 6 there and pause it any time.
Yeah.
It starts at 351.
351?
351.
So if you go to about 335 or so, then you have.
351.
Yeah, I'd say stop it at about 335 or so.
Okay.
And then we got about 10-15 seconds.
It's the ending.
And I'm going to press button 6.
Yeah.
Okay.
Press it.
Now, see it's flashing.
Okay.
All you've got to do is press button 6 there to start it.
Okay.
You might have to put your finger here though, because it's a bit slippy.
Yeah.
Okay, so next that was the bird song. Now we're going to go and do exactly the same. We're still on 2400 volts, and then we're going to play Bach.
Violin.
Bach violin.
Yeah. 5 bar. So, ready?
Yep. Okay, it's good. tube is much more stable than the other one.
Yeah.
And it doesn't blow out. And off on the HP. Okay, so what we're going to do now is we're going to move up to putting the power supply in series. So we move up from 2400 volts to 4800, and we see how large a flame speed we could make.
The burning bush, yeah, but we have to be careful with the modulation because I can't exceed 5,000 volts.
Yeah.
You're going to want to go up to about 6,500.
Okay, so you'll need to be careful on the modulation.
So put the light bulb back in.
Put the light bulb back in, and let's go back to getting the burning bush.
So get the burning bush, and then we go back to the birds.
You could just turn that off, or we'll reconfigure the...
And the obvious difference in this flame speaker this time is that it actually grows with the sound.
Yeah, that's why it's so distorted. So,
This-
but the thing is the modulator's making it operate in the pulsed mode. So if this was much higher frequency, the music would be making all these fractal discharges. But we don't have the power, and the frequency's too low. Seems like you got to get up to more like 5 megacycles to do that kind of stuff.
The advantage also of using this GU5B is the tube is much more stable on the oscillation, so it's much more capable of sustaining the oscillation even given the additional modulation bursts. I mean, it's actually much more stable than the...
Yeah, because when this thing goes over 100% modulation, it's turning the power supplies off.
Yeah,
There's no voltage on that too.
yeah,
And it's starting right up. It's not wasting any time
exactly.
going.
Well, it's what we said about this this form of Russian tube. Seems like it really wants to oscillate.
Yeah, because it's zero bias too.
Zero bias tube.
That's what's doing it.
Yeah, so it can start very easily.
Yeah.
Oh, good, an ideal system.
The flame won't grow this time because the modulation will not be exceeding the power of the flame. So basically, the flame will have a nice body to it, so the modulation will produce a much higher fidelity. It won't be crackling and intermodulating and what have you.
Okay, so we put the power supply
The bird's gonna.
back. Yes, okay. All you need to do is press the play, press button 6 again, okay?
Yeah.
When you're ready. Let's get the burning bush first.
Yeah.
Check, because we need to adjust the grid current and everything. Okay, so what we're going to do now is we've put the high voltage source into the series mode. So that will give us a nominal around about 4,500 volts plate voltage. We're just going to get the burning bush back again so we can make sure the system is nominally in its right configuration. Okay, Eric, when you're ready. Okay, let me just check rather long grid current. Just back it off a little bit. Okay, that looks okay.
Okay, so you ready to go with the modulator?
Yeah.
Okay.
Eric, it's
Yeah.
just that we will need to run for slightly shorter bursts now because the tube will get quite a bit hotter.
Yeah, yeah.
Okay?
And the music is, or the birds are ready to go?
Yeah, you just have to press button 6 and then switch over to the modulation.
See how much clearer it sounds?
Yeah. Can you go up in modulation slightly?
Yeah. Very clear.
Let the tube cool down. Yeah.
I'm going to let the birds go ahead to the better part. Then I'll turn it back on.
Yeah. Nice and clear.
Yeah. Yeah, that's what I'm trying to do. This in this way, the fidelity will be very high.
Yeah.
I think the double stopping violin will be much clearer
Yeah.
because that violin's playing 2 notes at a time. Bach is renowned for that, getting the violinist to play 2 strings at once.
Yeah.
I'm sure it's not an easy thing to do.
Yeah.
Yeah, now's when we need the big fan.
Yes.
So how many watts were we running?
We would have been running at about
Let's take a look.
4 kilovolts at 400 milliamp. Okay, so we're going to do Bach now on the 4800 volt flame speaker. First time. Okay, it's all good here. The fidelity is much better.
Yeah.
We just stopped there because the tube was getting very hot, but we could see basically the difference in the fidelity of the music that we got there from the 4800s flame speaker. Well, Eric, congratulations. That was a very, very good piece of work.
I do want to mention that when the flame speaker stops and you can hear music in the background, that's just this speaker at low volume back here, just so Eric can tell what's going on. But that's not where the music is coming from. In the flame speaker, it's coming right out of the flame at the top of the mast.
Well, I think now it's all static testing.
Yep. That was a very successful... Now we have to shake hands again for the camera. Look this way, Eric.
It worked.
It worked.
Success.
Very good piece of work. Well done.
Now it's 10 degrees hotter in here in the middle of summer.
Yeah.